Okay, looking at some properties of the dot product. We just addressed a couple of them here, but we got to be aware of what it means to prove a property of the dot product. So one property of the dot product, and digressing, dot product of u and v, in other words, u dot v, is defined to be, well, it's equal, first of all, to u1, u2 dot v1, v2, because u is the vector u1, u2, v is the vector v1, v2. The dot product is just first component times first component, u1, v1, plus the second component times the second component, u2, v2. Now, is it true that v dot v is equal to the square of the magnitude of v? Okay, well, in R2, of course, the magnitude of a vector is just how long it is. So if v1 is the x component, then that's how long the x component is. And if v2 is the y component, that's how long the y component is. The x component and the y component are perpendicular, so they form the sides of a right triangle, so that we have here the hypotenuse of a right triangle, one of whose sides has a length that's equal to the magnitude of v1, and the other a length that's equal to the magnitude of v2. So that we can write that the length here of the hypotenuse equals the square root of v1 squared plus v2 squared. And it doesn't matter whether v1 is positive or negative, and it doesn't matter whether v2 is positive or negative, because we're squaring them. Remember again that v1 and v2 are just distances, essentially. They can be plus or minus. These are just numbers. Okay. Now, is it then true that v dot v is equal to the square of the magnitude of v? And of course, this is, and what we calculated here, the hypotenuse is the magnitude of the vector v, where v is the vector v1, v2. Okay. Well, let's work it out. Okay. We could do v dot v. Here's v dot v. Okay. Dot product, first component times first component, v1 times v1 is v1 squared. Second component times second component is v2 times v2, v2 squared. So v dot v equals v1 squared plus v2 squared. Magnitude of v is just the hypotenuse of the right triangle with legs v1 and v2, as we illustrated up here. It's the square root of v1 squared plus v2 squared, just the way we calculated it. So, is v dot v equal to the square of the magnitude of v? Now, we're doing a lot of steps here, and you already see it, I'm sure, but let's just work through the steps to be sure. V dot v is, well, we calculated it up here, v1 squared plus v2 squared. Magnitude of v is the square root of v1 squared plus v2 squared, and we're squaring that. Well, the square of the square root of v1 squared plus v2 squared is just what? It's v1 squared plus v2 squared. So our equation becomes v1 squared plus v2 squared equals v1 squared plus v2 squared, and we'll put a big old check mark next to this one, and we'll erase that plus sign, and we'll put a big old check mark up here. This property is true no matter what the vector v is, because no matter what the vector v is, it's going to have a component v1 and a component v2, and everything we said here is going to have to be true of those components. Okay. Another property. If v dot v equals 0, it has to follow that v equals 0. In other words, if v is anything but 0, v dot v is not 0. Okay, well, that follows just from our Pythagorean theorem again, actually. If v isn't 0, then either v1 isn't 0 or v2 isn't 0. Now, it might be that neither one of them is 0, but at least one of them has to not be 0, because otherwise they're both 0, and then v is just a 0 vector. Okay, so if either of these is not 0, then either v1 squared or v squared ain't 0. And if one of these ain't 0, then the sum of the two squares ain't either. Ain't 0 either. Should be ain't 0 neither. Okay, well, again, seriously, v1 or v2 has to be non-zero. Okay, so either v1 squared or v2 squared has to not be 0. The other one can't be negative because it's a square, so you're going to have something that's greater than 0 added to something that might or might not be 0. Whether it is or not, whether that second number is or not, whether the second number is 0 or not, when you add them up, you're going to get something that isn't 0. Okay, so now think about whether that actually proves the statement. Okay, we could prove the same two statements, and I'm going to claim that it does. We could prove the same thing for vectors in R3. Okay, yeah, all we'd have to change is let u equal u1, u2, u3, let v equal v1, v2, v3, and then proceed as before. When we do the dot product, of course, we're going to have u1, v1 like we had before, and u2, v2, same as we had before. But we're also going to have plus then u3, v3. And if we wanted to do this in Rn, then we'd have all the way from u1 down through un, and v1 all the way down through vn. And we'd have n products here, okay, that would add up to our dot product. In any case, the arguments just follow as they did before. If you accept that the magnitude of v is the square root of v1 squared plus v2 squared, and if you got whatever number of vectors you have, you go to v3 squared, v4 squared, if n is greater than 3, and you end up with vn squared. So you just add up all the squares of the components to get the magnitude of the vector. Okay, if you accept that, then all this follows, and I recommend that you work it through to get in the habit of writing these things out, because it's probably not something that comes natural to you. It's probably not something you've had to do a lot in your education to this point. So it takes a little practice. Your book gives you many examples. You need to be writing some out yourself. And of course, they're being assigned, so hopefully you're doing that.